Okay, so today's lecture 12. So we're done with graph theory, and I sort of forgot, uh, what my agenda was earlier before graph theory. But anyway, so there's some pending items. So we are for sure done with graph theory. And I think I wanted to do some more theorems on permutations, but since this is the last lecture before this, uh, I just looked through the whole thing and then I realized there's one thing which is sort of pending, which I can do, which I had sort of promised that I will do, and let me do that. So today the principle of inclusion exclusion, and tomorrow morning I will upload the exam. So I've made the exam. I just want to sleep over it um, for upload the midterm, and then from next after break we will do mostly partitions. So we will begin partitions. So I looked through several introductory books, and more or less we have. I mean, in all of them we have covered something like. Um, I would say for the introductory parts, so approximately 50 to 60% of the topics are covered. I mean, I'm not counting the partitions part, and so now, I mean, I think so. This is good enough as a survey after this topic, and then we will do a deeper dive into partitions. So partitions meaning integer partitions uh, from most introductory books. So some more things from Wilf will come up, uh, while doing partitions. But we'll do partitions plus some number theory, some I would say. I mean, it's these are things which are not really covered. I mean, one of the goals which I wanted was to at least show you one theorem of Ramanujan with proof. So that is not usually covered in the combinatorics course. So I wanted to cover at least that much so that you know what all people are interested in. Anyway, um, so here's a theorem: the principle of inclusion exclusion. We've done one formulation. Let S be um, a set of objects, and let P1, P2, PR be properties. Which the elements may or may not possess. Okay. Um, let n of I, j, and so on numbers be the number of elements of S which possess properties Pi, Pj, and so on, Pk. and possess at least um, shall we say, just write a note here that they may possess more. So this is the number of this. Then the theorem says then the number of um, elements of S possessing at least one of the properties is problem goes on up to r minus 1 n. Okay, so this is an inclusion exclusion. You include all the properties, subtract so those which have just two, add more. So this have at least one, this has at least two, this has at least three. So you have at least one, then you subtract the ones which have got at least two, and then you add the one because they have got counted twice, and then you add the ones with at least three and so on. So this is roughly speaking the same as saying this union of AI is equal to summation AI. This is what it is actually. Yeah.
Fasno, are we saying they possess at least one property out of I to k?
1 to k.
I mean, I j k, something like that. So when we are saying at least one property, so is it like all P1 to PR or like
Yeah, yeah. All at least one of the properties. Yeah,
okay
from
P1 to
1 to
PR?
R.
Okay, okay, all right.
So this is, I mean, this is just a remark that this is roughly equivalent to what we've done earlier, saying that any element of A, which so any element of S which does not possess any property does not contribute anything to this sum. Okay, or rather contributes, uh, i.e., contributes zero. Now, suppose an element has t of the properties, R properties. Okay, then it contributes how much? When it contributes t to the terms ni. So this first sum, it contributes t choose 2 to the terms ni, comma j, and so on. It contributes t choose t to the terms ni, j, whatever. And there are t of them. Right? So let me say I1, I2, I3. So it contributes t, but here it contributes with a minus sign, and here it so all of them is some kind of sign is there. So its contribution is what is its total contribution? Its contribution is you sum up all these things. P minus P choose 2 plus P choose 3 plus so on up till minus 1 raised per P, P choose T. Or 1 minus 1 minus T plus P choose T. So this is T minus 1 here. And this is 1 minus 1 raised per T. So it's 0, so it contributes 1. So any element which has you know T properties, then it contributes 1 to this sum. So if it doesn't have any property, it contributes 0. If it has some property, it contributes 1. And therefore the total number, this number right here, so the sum is equal to sum over all elements which have some property, P1 through Pr. And that's exactly what is number of is number of elements with at least one property. So this same sum which came out earlier in our thing comes out here. So that completes the proof. And before I take any questions, this is the usual form. The usual form of this is that the number of elements of S possessing none of the properties P1 up till PR is the number of elements in S minus the summation Ni plus the summation Nij plus minus 1. So plus minus 1 raised per R and 1 to R. Just thinking this is, yeah, minus R. Okay, any questions? So this is called sieving. So why is it called sieving? Any questions so far? Any questions? Okay, so here's an example. You want to let us find the number of just to explain the term sieving, we find the number of primes less than equal to 100. So any number uh, which is less than 100, which is not a prime, is divisible by a prime number less than equal to 10, because square root 100 is equal to 10. So it's divisible by 2, 3, 5, or 7, right? So let's look at this property P1 be the number of the property that um, number is divisible by 2. Let P2 be the property that the number is divisible by 3. Let P3 be the property the number is divisible by 5. And P4 be the property that number is divisible by 7. And let N1 is the number of numbers less than equal to 100 not divisible by 2, so that's 50. And 2 is divisible by 3, that's how much? 33. And 3 is divisible by 5, that's 20. And 4 is divisible by 7, that's 14. Right? 14 into 7 is 28. Okay, so let's do N1, 2. This is the number. So these are divisible by, so this is numbers divisible by 2 and 3. So, or divisible by 6. So how many are there? 100 divided by 6. Similarly, 1, 3 is the number of divisible by 2 and 5. So that's 10. And 1, 4 is the number divisible by 14. That's 7. Uh, 2, 3 are divisible by 15. That's 6. 2, 4 divisible by 21. That's 4. Then we have 3, 4. They're divisible by 35. So that's 2. So, yeah, how many are these? All these up till here. 26, 32, 39, 41, 45. Okay, then we need things which are 1, 2, 3. So numbers divisible by 1, 2, 3, which is 2, 3, and 5. So that's 30. So there are 3 of them. 1, 2, 4, 2, 3, and 7. That's 42. It's 2 of them. 2, 3, 4 is too big. There's nothing divisible there. 1, 3, 4. That's um, 7. Yeah, 70. So that's one of them. So these are 6 of them. So the total number. So how many are these? Um, 83, 103, 117. So these are 117. So the number not divisible by 2, 3, 5, and 7 are 100 minus 117 plus 45 minus 6. Right? So this comes out to so 22. So this includes 1. So there are 21 plus the 4 fine. So 21 are prime plus the 4, 2, 3, 4, 7. So total number of primes is 25. So if one notices this number, it keeps reducing. So this is bigger, then this is smaller, then this is bigger, then this is smaller, right? So you can stop at any given point and see and get some estimates. So that's the idea for a lot of number theoretic estimates, that you can sieve off numbers divisible by 2 and 3. I mean, you can try this for 1,000 and just do for these few things, and you get some estimates. And that's what they try to do. They try to get some estimate of the total number of primes when the number becomes quite large. So that's the idea for getting a large. So if you just stop at, let's say, just these numbers 2, 3, then take the estimates. That would be like sieving the only those guys. Okay, any questions so far?
Professor, if we calculate exactly, then we get exact number. Otherwise, if we estimate, then that will be estimation, right?
Yeah. So I mean, this formula basically, each term becomes smaller and smaller.
Right,
So when you do Eratosthenes sieve, the idea is Eratosthenes sieve is exactly this, right? It's, suppose you have uh, so what you do is you cancel all the numbers which are divisible by 2, right?
right, right,
So as a first estimate, whatever are the remaining numbers could be a first estimate for the number of primes,
right.
less than 20. 1, 2, 3, 4, 5, 6, 7, 8. Right? So the 8 is the first estimate. Now let's remove this guy. P, right? So we get how many? 1, 2, 3, 4, 5, 6 primes. This is the real guy. This is the correct amount. And this is the first estimate. Right? So square root of 20 is about 4. So this covers all the primes. So when you talk about sieving methods, you try to say that, okay, can we get an estimate? And each time you have a smaller and smaller thing. So you got 8 minus 2, right? So this is a smaller number than this guy. Yeah. And so you can sort of estimate it by taking the largest few numbers. So you divide numbers by 2 and 3 first. When large numbers drop out, then you divide by 5, and then smaller numbers divide. That's right. So I mean, same principle, but this is very useful principle. And that's the reason why I wanted to cover it, because you will see it in many contexts. I mean, so this the generating functionality approach doesn't quite sufficiently tell you about this technique. So that's why I wanted one lecture on this idea. So you will see it again and again in various contexts. So in fact, um, um, my PhD advisor, um, so his name is Steve Milne, and he wrote a paper along with his advisor, and that guy's name is Garcia. So Garcia and Milne gave a first sort of combinatorial proof of the Rogers-Ramanujan identity. We will cover these Rogers-Ramanujan, not their proof. And their proof involved what they called the involution principle, which I hope to cover at some, because uh, I want to learn it myself for one thing. And this is a extension of uh, principle of inclusion exclusion. It is called pi. So this has become like a central piece of their whole. This involution principle has become like a central piece of mathematics after their proof. So this proof was in 1980 or something. It's called Rogers Ramanujan bijection. But this principle came out, and this is a very so this is very subtle, and most of number theory, the sieve methods and all are take off from here. So one needs to understand this and look at it. So we'll see some examples. Anyway, um, so example is counting surjections or onto functions. Okay, so from x to y. So let x be n, y be n, and let y be in fact y1 through yn, and f be a function from here to here. Uh, and how many, the question is, how many f are onto functions or surjections? So just to remind you, onto means for every for every y in y, there is an x in x such that f of x is equal to y. Okay, so let S be the set of all such functions, set of all functions uh, f from x to y. So how many number of elements? So you have 1, 2, 3 up till m, and 1, 2, 3 up till n. So all these guys are mapped, right? So possibility of one is, it can come in any this one can come in get any one of the n values. So the total number is n raised per m. Yeah, because each chap here can get n possible values. This guy can get n possible values and so on. So by the multiplication principle, this is what it is. And let pi be the property that yi is not in the image of f. So n1 is the number of so what is n1? So y1 is not in the image. So n minus, so this many can be in the image. So each element can be mapped to the remaining -1 elements. Then n2, so you choose two elements. Number of ways of choosing two elements here which are not, and then n minus 2 raised per n, and so on.
So, Professor,
Sorry, not n2.
similarly for n1, we'll get a factor of n, right?
Yeah. So, um, and yeah. So for one particular I, you get this, and so I'm wrong. Let me write it as ij. Now this is correct, right? Particular. So given fixed two of them, then it's n minus 2m. And let's say fixed I1, I2 up till I some k of them, it is n minus k raised to n minus k raised to the power n. And this is for a fixed guy, right? This is for a fixed chat. But when I'm doing the sums, so the sums, the required number is equal to s minus the sum over ni plus so on. That will be n raised per m minus n choose 1 of n minus 1 raised per n plus n choose 2 minus 2 raised per n. So the last guy will be minus 1 raised per n, n choose n, and minus n raised per n, right? So this is summation minus 1 raised per I, n choose I, and minus I raised per n, I going from 0 to n. I mean, the last term is 0, so one could do minus 1 also, right? So this is the required number, and immediately we have a corollary that when n is bigger than m, this number has to be 0. Because, you know, there are n here in y and m here in x. So it can't be surjective. So this sum in choose I n minus I raised per m has to be 0 for I going from 0 to n minus 1 if n is bigger than m. Okay, so there's an alternative way too. Um, any questions so far?
Can we say anything about n when n is equals to m?
Yeah. I'm just going to do that. Yeah, we'll figure that out very shortly. So there's an alternative approach. So recall Stirling numbers of the second kind. This is Stirling numbers of the second kind. And this was a number of ways of partitioning uh, an n set into k parts. Yeah, so what we could do, an alternative approach is you partition x into k parts. So x1 up till xk, right? And you choose for each of these, you choose an image set uh, of size k. So choose in how many ways can you do that? You choose n minus n choose k take, and then you pair each of these, pair each of xi's with uh, you know with this image set in k factorial ways. So this will mean that number of functions uh, f from x to y with image size k is s n k times n choose k times k factor. And the total, and this also means, so if you then you sum over all the function. So that means that the total number of functions, which is equal to n raised per m, has to be the sum of all these Sn k and choose k factor k going 0 to n, right? So this is one, and if k is equal to n, the image size is equal to n. So if this k is equal to n, that means number of surjections. Then this will give you the number of surjections that will be equal to S n k, n choose n, and n factor. So S, this is m or n. So there is some confusion here because I've got an n set here and an m set there. So there's some confusion here now. So here I'm taking n set, and there I had a x in had m elements. So let me change that. Sorry about that. Let me change it to m. And this is fine. Uh, this is fine. You're choosing an image set of size k from y, and this should be m, and this should be m. So this should be m. Okay, is this clear? So I messed up here. This x was m, number of, so our x in the previous example was m, and here I'm choosing an n out of k. Yeah, this is fine. Okay, so what does this give us? This gives us Smn n factorial should be equal to what we got earlier. Now, if you recall, this is, remember, this is some sequence ak times n choose k, k going from 0 to n. So you can get this from, you can get 2 from 1 by matrix inversion 2. So there's an extra sign, and then, I mean, you have to replace I by n minus I, and then you will get it. Replace I by n minus I, and you will get it. So this was, remember, up till n. So this chap, Snk, k factorial is your ak. This is of the form n choose k ak, right? And this is of the form an is equal to minus 1 raised power whatever. So you can get this from your inverse relations too. But you have a formula. Okay, any questions on this?
Professor, I was thinking, like when you stated the question first, I was thinking if we approach the question using the basic counting principles, the multiplication rule. So what if we approach it like this? So first we choose n elements from the set X. So we can do that in m choose n ways. Then for each choice of n elements, we can send them to n factorial, like we can send them surjectively to y in n factorial ways. And then the remaining m minus n elements, we can send them anywhere. So like the total number of functions would be m choose n times n factorial times m minus n to the power n. Like, would that be a correct approach, or would there be double counting somewhere in there?
I mean, you try it out. It should be pretty clear for just two or three. I mean, try a small case, and it should be clear whether it's working or not. Um, so
Okay,
traditionally,
Professor.
I mean, I haven't really solved the problem on my own. I don't think, but traditionally, I've always seen subjections coming in this plus minus way. The other way is to look. This is the more direct way over here. This alternative approach is the more direct thing. That you're taking this x and you're chopping it into k parts, and you're taking this into k parts, and then you're mapping, these two guys together somehow, and the image sets.
Okay.
Yeah.
Thank you,
But
Professor.
I mean, just try it out, see what works. Okay, so let's look at one more number theoretic example. So again, this is where it comes out. So this is known as the Euler quotient function. So this is in number theoretic context. This um, how inverse relations come out, and this is very important. So let phi of n be the number of uh, integers uh, k less than equal to n, uh, which are relatively prime uh, to n. So have you seen this function? So phi of 1 is defined to be equal to 1, and phi of 2 is defined to be equal to phi of 2 is 1, because only 1 is the only element which is phi of 3 is 2, because both 1 and 2 are relatively prime to 3. Phi of 4 is also 2, because 1 and 3 are the numbers. Phi of 5 is 4. So 1, 2, 3, 4 are all relatively prime to n, 5, and so on. So in fact, for any prime p of p is p minus 1. And phi is a number theoretic function. What that means is that phi is a function on n to something. So it's number theoretic uh, to R or C or whatever. And it's a multiplicative function, which we will shortly show. What that means is that phi of n times m is equal to phi of m, if n and m are relatively prime. So sometimes I write GCD as just km. So if I forget to write GCD, it means the GCD. Okay, so we want to calculate that. So let n be some p1 raised per a1, p2 raised per a2, pk raised per ak. Let's calculate phi of n. So phi of n is, so it's the number of numbers not divisible by any of p1, p2, pk. Right. So if we use our principle of inclusion exclusion, it's n minus the number of numbers which are not divisible by any pi. So this is the as which is not divisible by pi. Uh, then numbers not divisible by pi pj minus pi pj pk and so on. Right. Now if you think about it, this is 1 minus 1 over pi. I going from 1 to. So n is common here, and then when I multiply it out, uh, 1 minus p1 times 1 minus p2 times 1 minus p2, p3. So this is 1 over 1 minus p1, 1 over 1 minus p2, and so on. So I'll get these terms alternate with alternating sign. If I have got I of these or R of these terms, I'll get minus 1 raised per. Is this clear? So in particular, this shows that if uh, uh, p of p raised to the power some r is p raised per r minus 1 times p minus 1, because n, uh, well, it's p raised per r times 1 minus 1 over p, which is equal to p raised per r minus 1 p minus 1 from this form. And it shows that if n and m are relatively prime, then clearly P of n times m is, you have n into m product of 1 minus 1 over p, p divides n, and product 1 over 1 minus q, q divides n, q prime. Because they're relatively prime, these primes are not common. So that's P of n. Okay, so this shows that phi is multiplicative, and this particular story comes up a lot. So I'm going to do more of where phi comes in. So let's go. Any questions so far? Any questions? So some generating functionality which works in which is useful in functionology. Um, Let an be a number theoretic sequence. So this is how it happens in number theory. And some of the same ideas apply. So that's why. So suppose G of S is summation a n raised per s, n going from 1 to. This is the function, I would say, is called the Dirichlet, Dirichlet, it's Dirichlet generating function of a n, of Why am I writing G? Right, A of S. So let B of S be summation B of S over N raised to S. B of N. Right? So then what is AS times B of S? So let's just work it out. It's A1 plus A2 over 2 raised per S plus A3 over 3 raised per S plus A4 over 4 raised per S times B1 plus B2 over 2 raised per S B3 over 3 raised per S. So the first term is A1 B1. Now you'll have this 2 raised per S will come in uh, A2 B1 plus A1 B2 1 over 2 raised per S. 3 raised per S will come on A3 B1 plus A1 B3. 4 raised per S will come in A2 B2 plus A1 B4 plus A4 B1. So you get the idea. The idea is that it is the sum over AD Bn over D of D divides N 1 over N raised per S. You get that? So each term inside is the divisors of 4. So 2 and 2, 1 and 4, 4 and 1. Yeah? Is this clear? So number theorists, um, uh, if if A and B are number theoretic functions, that means A and B are defined on N, something to complex numbers, then this they call the convolution, the Dirichlet convolution, AD Bn over D. So I'm just writing it as subscript, but they can write it whichever. So, and D divides N. Okay, and this is known as a Dirichlet convolution. And this is commutative. It is associative. It's very strange that I use the same terms that I'm using in my calculus class every day. This class, something going on. And the identity element is this function in, which is the greatest integer in 1 over n, which is basically 1 if n is equal to 1 and 0 otherwise. Okay, so phi of 1 is just, it's not even there typically. You just do it for this. So this is the identity, and there is a function called u of n for all n. This is a unit. Uh, yeah, this is also an invertible element. So there is this whole theory of this is a ring and what its inverses are and so on. but that's not totally relevant to us. I mean, at least not now. Uh, so mu of n is called the Mobius mu function. This is a very important function, and this is defined as follows. Mu of 1 is 1, and mu of n is 0 if n is not a square free number, and it's minus 1 raised per k if n is p1 to pk. So if it has any square of some prime, it is 0. Otherwise, uh, it is the product of the number of primes. This is the number of primes. So minus 1 raised to, so it's a signed function. And the proposition is mu of d is equal to I of n. D divides n. Okay, so what this means is mu star u is equal to I. So this function, the inverse of this function in some sense is this Mobius mu. Any questions so far on the definitions? Any questions? This is mu of 1. So I mean, if you want to calculate mu of 4, what is mu of 4? 0.
0.
Mu of 15 would be
1.
because there are two primes, 3 and 2, right? So it takes getting used to, but this is precisely what we'll know exactly why this function is important very soon. So for n equal to 1, it's fine. This matches because in is, remember, 1. So if you do mu 1, that's equal to, by definition, mu 1 is 1 and this side is 1. So suppose n is bigger than 1, right? So this function d divides n, mu of d. So we might as well just say that this is equal to mu of d, where d is square free. Because when d has squares, then it is 0, right? So d divides n, but d is square free, right? So then this is what? This is mu of 1. Let's say the first term is mu of 1 because d equal to 1. Then it is mu of p1 plus mu of p2, whatever we are doing, plus mu of pn. So I'm assuming, say, n is equal to p1 raised per a1, whatever, pk raised per ak, like we were doing earlier. And plus mu of p1, p2, mu of p2, p3, so on, right? So what is it? It is 1 plus these guys is a single thing. So you're choosing one prime out of, k of them. So k choose 1 with a minus 1 sign, plus k choose 2 out of these primes. And again, same story, whatever our story is. Minus 1 raised per k choose k. Right? So this will be equal to 0 because this is 1 minus 1 raised per k, which is 0. Right? So for if n is bigger than 1, then we get the same 0 story. So you can see, I mean, it's the same thing, but maybe in a different language. So what we have is mu of d d divides n is equal to 1 for n equal to 1 and 0 otherwise. So the proposition, what does it mean? So the proposition means mu star u is equal to I. So mu is invertible in the ring, right? Right. So what this means is that in terms of generating function, what does it mean? So remember, generating function of this guy is -1. Uh, this well, let's just look at this. So summation of u of n raised per s. So Dirichlet function for u of n going from 1 to infinity. So u of n is just 1, right? So have you seen this function before? This is the Riemann zeta function, right? And this other function. So what is this story saying? This is saying that mu of n, n raised per s, n going from 1 to infinity times summation 1 over s, n going from 1 to infinity is going to be equal to um, summation I of n, n raised per s, n going from 1 to infinity. But I of n is just 1, right? So I of 1 is 1 and rest are all 0. So this is what it's saying. What this is saying is that this guy right here is 1 over zeta of s. So that's the significance um, of mu. And further, okay, suppose a of n is uh, this is given like this, then what this means is that a n raised per s n going from 1 to infinity is equal to summation n going from 1 to infinity d over n dt times 1 over n raised per s. And this guy is a convolution of uh, what? It's a convolution of bn over n raised per s multiplied by summation un, which is zeta of s, right? So this means that summation bn over n raised per s n equal to 1 to infinity is summation an n raised per s multiplied by 1 over zeta of s. 1 over zeta of s is summation mu of n raised per s. So what do we get here? When we again do the convolution, it's mu of n, a of mu of, let's say, n d, a over n by d, d divides n, 1 over n raised per s, yeah, or the other way around. Or you can just write d divides n, mu of n by d, a d, 1 over n. So what does this mean? So we get b of n is equal to, so you compare the coefficients, b over n, mu over n by d. So we have shown, well, I already had 1 and 2, let's call it 3, 4. This is equivalent to A of n, B divides n, A of B. This is 3 again. So this is known as, this inversion is known as, um, this is known as Mobius inversion. So one can see it is very central to um, number theory, right? So any questions? So let's just look through back. We are saying that um, I mean this number theory part. Just a quick overview before I go ahead. Uh, you have this function phi of n. You have this function mu of n, and defined like this, and you have then this relationship that if any two sequences are related, then so this mu of b um, helps you invert this kind of relation. So mu is a plus minus kind of business. It's like plus minus 1 of n choose k, and this is so it's the same idea, same principle, same everything, and in fact we're using the same binomial theorem. In all three cases, we are using the same thing. So it's really equivalent, but different ways of looking at it. And this has to do with Dirichlet generating functions, of which the prime example is the Riemann zeta function. So the Riemann zeta function is the simplest of all these number theoretic functions, Dirichlet, which is just one, you know, on all n. So u is 1 for all n. This is the simplest of all possible number theoretic functions, and the zeta, uh, you know, so Riemann zeta function comes up as a Dirichlet generating function of that, and it is so involved in its inverse is involved in doing what is called Mobius inversion. Okay, so we had proved this earlier. I'll just go over this again. We actually had proved this. What did we show? We have already showed that P of n is equal to summation mu of d n over d. Where did we show this? We showed it right here. If you look at this guy, so what is this minus sign? This is n over d, and we basically used only those d which have some kind of positive value for mu. So it's minus 1 raised per mu, and this was b and so on. This is already done. So what does this mean? So if you invert it, inverting, you get inverting using Mobius inversion. This is an example, elementary example. So I mean the connection should be clear. The connection should be 100% clear that why Mobius inversion is essentially the same as principle of inclusion exclusion, which is just the same as this is binomial theorem. This identity that summation n choose k minus 1 raised per k equal to 0 for n greater than 0. This is the identity at the heart of it. This is a trivial fact that this is 0, right, for n bigger than 0. Okay. Any questions? Yeah, one more theorem before I stop for the day, which I won't prove, so it's okay. Let f be a multiplicative number theoretic function. Then, I mean, one can prove this also. Then formally, summation fn over n raised per s is equal to product over p 1 plus fp p raised per s plus fp square p raised per 2s plus 1. So the proof is omitted. I'll do an example. Okay. So let us look at uh, this thing. Beta of s is equal to summation 1 over n raised per s. So let's look at this guy. What we do is we multiply both the sides by 1 minus 2 raised per s. So if I multiply this guy by 1 minus 2 raised per x, 1 half raised per x, then I multiply this guy with and so on. So what's happening here is that this guy gets cancelled, and this will get cancelled with 1 over 4 raised per s. This will get cancelled by this. So it's sieving. It's doing the same old thing. It's sieving, and what you're going to get is 1 over 1 plus 3 raised per s. You're going not going to get 4. You're going to get 5 raised per s. You're not going to get 6, but you're going to get 7 raised per s, and you're going to get 9 raised per s, and so on. So all the even numbers drop out. Now suppose I multiply by 1 over 3 raised per s. I'll get from the first term I'll get 1 over 3 raised per s. From the second term I'll get 1 over 3 raised per s, or 9 raised per s, plus so on. So now this is cancelling. Now this guy is cancelling. So what do I get? I get 1 plus 1 over 5 raised per s. So I get rid of all the things which were divisible by 3 now, which had not previously been cancelled. So I don't have 6, I'll certainly have 7. I won't have 9, I'll have 11. And I won't have 12, 13 I'll have, and so on. So if I keep doing this, then I will get zeta s times 1 over 1 minus p raised per s, p a prime, and in the end I'll get 1. So zeta of s is equal to products of p 1 minus 1 over p raised per s minus. So this is formally true. This is Euler's, uh, this guy is called Euler's product formula for the zeta function. So yeah, any questions on this? So this is something which I told my calculus class. I don't know if you would have seen it. Euler's proof that primes are infinite. So suppose not that P1, Pk be all the primes. Then consider 1 over 1 minus 1 over Pi, which is equal to 1 plus 1 over P1. This is I plus P1 square, so multiply all of them. Then since every number can be written as a product of primes, this is going to be summation 1 over n in a unique way, and this diverges, but this is finite. That's a contradiction. Okay, so that's it for today. After the break, we'll do partitions, more of that. I mean, there is sufficient material uh, to do for 6 7 weeks. We'll see. We might go a little slower than we've been going, but I wanted to give you an idea about the depth of the subject. So all what we've been doing is like 1 month theorem in one area. So there are like 15 20 areas which have been covered. Um, but what we want to see is something, you know, some more depth. So okay, any questions?